Hello viewers, now I will discuss this important idea of orthogonal complements. At first stage, we going to define what orthogonal complement is, and very important notation I will discuss, which is very much useful in this part. Let's watch this video till the end. And the viewer who are watching this video first time, subscribe the channel and press the bell icon to get all the valuable notifications. Now at first we are going to define the part of orthogonal complement. Let's watch. For the part of definition, at first we are going to take a set, simply a set. So let S be a non-empty subset of Hilbert space. Actually, here we conceptualize everything in the space. So it is a media of Hilbert space, and taking this space we are taking, better to say, a subset. Under this Hilbert space H, we are taking S be a subset. So let S be a non-empty subset nature of Hilbert space H, and the orthogonal complement of S we are going to define or retain it as S perpendicular, and read it as S perpendicular. So S reverse T, that is a perpendicular notation. S perpendicular, and is defined as S perpendicular as X belongs to H. X is a vector concept in Hilbert space X H, and such that X is perpendicular to Y for all Y belonging to S. This is our definition part, and this is a helpful definition. Always remember it, and in many purpose we use this notation. And thus ST, S perpendicular, is the set of all those vector in H, that's a vector concept in Hilbert space H, which are orthogonal, that's a part of orthogonal, and which are orthogonal to every vector in S. This is very much important. And here if we notice, at definition S perpendicular, here X belongs to H, and we are taking X is perpendicular to Y. For Y, the nature of all vector in Y, that's the nature of all vector like Y, is belonging to non-empty set S. So in this way we are defined. Now I will discuss very important theorem in this part. Let's watch. And let S be a non-empty subset of a Hilbert space, non-empty subset of a Hilbert space of H, then S perpendicular is a closed linear subspace of H. So S perpendicular is a closed linear subspace of H. This is a very important theorem. Let's watch this theorem. Now we have, by definition, S perpendicular is equal to X is belonging to H, and X dot Y is 0 for all Y belongs to S. As per definition, we can show it, and this result, and since 0 dot Y, that is, if we take it 0 vector, that's a trivial cases, and certainly it will be 0 dot Y is 0, and for all Y belongs to S, and therefore at least 0 belongs to S transpose, and this non-empty, and thus S transpose is non-empty. And the next stage is, let x1 x2 belongs to S transpose and alpha beta be any two scalar, then x1 dot y, if we take x1 x2 belongs to S transpose, then taking inner product x1 dot y, and that will be by definition 0, as we take x dot y is 0. So x1 dot y is also 0, and for all y belongs to S, as per the definition of S transpose. And similarly, and we can write it as x2 dot y is also 0 for all y belongs to S, therefore y belongs to S, and taking the property of like a vector space property, we are taking to prove this result in this manner, to prove the linearity property. That's taking in this way, linear combination alpha x1 plus beta x2 dot y using the linearity property. That can be written as alpha x1 dot y plus beta x2 dot y. And as inner product notation, we can write it as simply alpha into x1 dot y plus beta into x2 dot y. It is simple because alpha, we can write it as alpha x1 dot y in this different type of component. We can taking in this manner. And as x1 dot y is 0 and x2 dot y is 0, so it can be written as alpha dot y plus beta dot y, and it will be 0. And therefore we can write it as alpha x1 plus beta x2 also belongs to S perpendicular as per the definition of construction of S perpendicular. X belongs to H, x dot y is 0 for all y belongs to S in this manner, and hence S perpendicular is closed subset of H, and we shall prove it by showing that if x is any limit point of S transpose, then x is belongs to S transpose, that is x dot y is equal to 0 for all s y belongs to S. Since x is a limit point of S transpose, we can write in this manner, and since x is a limit point, then x is belongs to S transpose and x dot y is 0 for all y belongs to S, and therefore as we say that x is a limit point of S transpose, therefore certainly there exists a sequence. We can take it here as a sequence xn of the points of x transpose such that xn tends to x. That is the limiting point. As we take it that xn tends to x, that is x converges, xn converges to x as a limit point, convergence sequence we take. And now let y belongs to S. Since xn belongs to x transpose, for every n, for every member of n, like x1, x2 in this manner, all n, like the formation of induction method, and therefore xn dot y is 0 for every n, and consequently we have taking limit xn dot y is 0, and that's included in this tag, that is xn, limit xn dot y is 0, and as limit xn is x, so x dot y is 0, and thus if x is a limit point of x transpose, then x dot y is 0 for all y belongs to S. Therefore x belongs to H transpose, and hence S transpose, that is S, here it is a S perpendicular, not transpose. We can write it as S perpendicular. S perpendicular, we are pronouncing it quite wrong. S perpendicular is a closed subset of H in this manner. So finally prove our desired result. So in this way we can prove this theorem. This is a very much important theorem. In this part we end our discussion today. If you like this video, like it, share it, and always subscribe the channel. Thanks for watching.